Equality of population means with equal assumed variances. This hypothesis test assumes that the two populations are independent of each other, but that their variances are approximately equal. So the best way to grasp this is by looking at a real-life example. Suppose that we're comparing the average of CFA exam scores in Toronto with that of the average of CFA exam scores in New York City. Now here's the observation from this example. The two groups are independent because each contains a different set of candidates. So you can't have a candidate that is simultaneously writing the CFA exam both in Toronto and New York at the same time. So that establishes the independence of the two samples. At the same time, the variances of the two groups are assumed to be equal because they are both writing the same exam. So it's not out of reach to assume that the variance of the two samples are equal because it's the same exam. So then how would we conduct the hypothesis test in this scenario? And again, always keep one eye on the big picture. What we're trying to determine is the equality of these two populations. So we want to know if the average score is the same, or maybe it's higher in one location versus the other. So there's a real life implication in this. So here are the steps. As always with a hypothesis test, the first step is stating the hypotheses, the null and the alternative. So suppose that the hypothesis is that the average score in Toronto is equal to the average score in New York City. Now the thing with hypotheses is that we need a numerical value for the hypotheses. So I don't see a number here. So we need to restate that so it does equal to a number. So if they're equal, then the difference should be 0. Now that's a numeric value that we can test. And there it is. So the null would be that the difference between the two is equal to 0, which in turn implies that the average at both locations is the same. And as always, if you reject the null, then you just go with the alternative, which would be the complement. So if you reject that they're equal, then it must be true that they are not equal, and that makes sense. The second step is to determine the level of significance. Now this will generally be given to you, and the level of significance determines the width or the acceptance range for the null. And in step 3, we have to determine the distribution for this sample. And since this test centers around sample mean, it's either a choice between Z or T. But generally for hypothesis tests, like almost 90% of the time, we use the T distribution. Now on the exam, the only way we can use the T distribution is if they give us the T table or excerpts from the T table. And then step 4, we do the test itself. Now with hypothesis test, I always liken it to penalty kicks. And the similarities are striking. So how does a penalty kick work? So suppose that's our field, and that's so that'll be the middle. What we're going to do is we're going to set up goalposts on either side. So this will be our goalpost right there, and so you can see how it looks like a net. So if the ball goes inside the net, that's a goal, of course. And if the ball goes outside the net, then it's not a goal. What's that got to do with hypothesis test? Well, the ball is really the sample. So if the sample falls anywhere within that range, it would be a confirmation of the null. But if the sample falls anywhere outside of the net, then it would be a rejection of the null. So then what we have to do, again, this is why I call it penalty kicks. You can see right there, we have to find the goalposts. Now in the context of hypothesis tests, the goalposts are really the critical values. And the critical value tells us basically how far we need to deviate from the null in order to construct the desired acceptance range for the null. Now to get the critical value, we have to specify the degree of freedom and the single tail area. But since we have two populations here, the degree of freedom is equal to the sample size, so the first sample size, so we're looking at Toronto, -1, plus the second sample, which would be the number of students you observed in New York, -1. And tip, and we saw this from a previous module, if the null hypothesis has an inequality, you make it a one-tail test. And therefore, the single tail would have the entire level of significance. On the other hand, if the null has an equality, that means we have to accept values equidistant on either side of the null. Then this would be a two-tailed test, and therefore what we have to do is we have to take the level of significance and divide it by 2. Now, again, sticking with the penalty kick analogy, after we've determined the goalposts, and again, this is a really good visualization here. Okay. And so now we have to determine whether the sample falls within the goalpost or not. Now, to calculate the sample statistic, basically what sample statistic for a single population told us is, how far does the sample deviate from the hypothesized value measured in standard errors? But since we have two populations here, look at the modification. Instead of a single sample mean, now I'm looking for the difference between the two sample means. And instead of one hypothesized mean, I'm looking for the difference between the hypothesized means. So do you see how I'm using this base case as a template to come up with the sample statistic when there's two populations involved? Now, what's the other modification? Let's look at the denominator. When you have a single population, I'm just interested in the standard error of the sample mean of that single population. But when you have two populations, here's what we need to do. First of all, remember that one of the assumptions here was that the sample variances of the two locations was equal. So then what we're going to do is we're going to use what's called a paired variance, which in effect is the weighted average variance of the two samples. And that kind of makes sense, ladies and gentlemen, because if the assumption is that the two populations have the same variance, then we should just use one variance for both samples. Now, how do you find that one variance? Easy. It's the weighted average of the two sample variances, right? So there it is. You could see me doing that right there. So the sample paired variance, again, it's the weighted average. So what's the weight of the first sample times the variance of the first sample plus the weight of the second sample times the variance of the second sample? And how do you find these weights? It's basically the size of the first sample divided by the total of both samples. And same thing with weight 2. You look at the size of the second sample and you divide it by the total sample, the total number of observations of both samples. So once you have the sample variance, it goes in there. So you see how you're representing the two samples, but you're using the same paired variance for both samples. So the only uniqueness for each sample is the sample size of each sample. So that's where you get N1 and N2. And then once you have, now remember, this is variance format, right? This is variance format, but I need standard deviation format, no problem. So once you figure out what the value is within the bracket, you take its square root. So that's it. That's it. That really is it. So what do I recommend you do on the exam? Do not memorize this at all. Instead, start with this and use this as a template and just tweak it in order to come up with that. Okay, so then what would be the decision rule? And this is the same for all hypothesis tests, ladies and gentlemen. So this decision rule is universal. If the sample statistic falls within the critical values, we would accept the null. And so this is where that penalty kick analogy comes in. So if the sample falls anywhere within the critical values, what we say is that after we factor out sampling error, it's possible that all these samples are a confirmation of the null. However, if the sample statistic falls outside the critical values, so if the sample comes here or somewhere there, we say, wow, these samples have really deviated from the null, and this is not margin of error because the margin of error stops within these bounds. So if the sample is coming here or there, that's because our sample does not support the null hypothesis, and therefore we would reject the null, and that's exactly what we have. But of course, if you reject the null, then what you're really doing is you're accepting the alternative. And let's just have a quick look at what the null and the alternative were. And this is what we're saying. We're saying if you reject this, then by default you're accepting that. But what does that mean in English? So if you're rejecting the equality of the two means, then what you're really saying is that the two means are not equal. And that's what we're really indicating by accepting the alternative, is that we're saying that the two population means are not equal.